Math 2414, Calculus 2, Section 9.2, Calculus with Parametric Curves, Video 5 of 9, Area. You'll recall from the end of Calculus 1 that the definite integral was a consequence of attempting to find the area under the curve of a graph. There are other applications, but that's one of the primary ones. What's the area under this curve from x0 to x1? Normally called a and b, but I'm using that in a different context in this example. Well, how can we think about this from the perspective of parametric equations? Well, before we talk about how to find the area under a curve that's defined parametrically, we need to clarify something. Because the x values and the y values on a curve are independent of each other, but rather dependent on a third variable, the parameter, t, theta, whatever it's called, there's no guarantee that the x has to always move from left to right, like in a standard function. Because the x can change direction, your curve can go left and right. For example, if we had a curve that started like this, but then its x values changed, how would we define the area under that curve? Until the point it turns around, it makes sense. It's this area here. But once it backtracks, are we like bending a piece of paper backwards and when finding the area under there? Will that area be positive? Will it be negative? Will it cancel out? What about this part where it doubles up? Because under here, it's also underneath the curve as it backtracks, as well as under the curve before it turns around. In order to avoid this, we're going to require that when we find the area under a parametric curve, that the x doesn't change direction. In other words, either the x constantly moves from the left to the right, or the x moves from the right to the left. And we can check this by looking at the derivative of the x term. If the x is always increasing, then its derivative should be greater than 0 on some interval a to b. Or if your x is always going backwards from right to left, then the derivative should be negative because your x's are decreasing on that interval. So when we find the area under a curve defined parametrically, we are working under the presumption that the derivative of the x doesn't change signs. Either it's always positive or it's always negative. So let's take a look at what would happen if the x derivative were always positive. If the x derivative were always positive, then we would have a graph that starts at some point. We'll say at, well, this is an x equals a, this is at t equals a. And then if the x derivative were always positive, then the x would always be increasing, so the x would always be moving left to right. Now the y can do all kinds of crazy stuff, but the x would always move from left to right. However, if the x derivative were negative, then wherever the curve starts, we'll say over here somewhere at time t equals a, because the derivative of the x coordinate is negative, the x parametric equation is negative, then the x values would always be decreasing, and hence the graph would move from right to left. My apologies, I should be putting orientations on these graphs. Arrows pointing the direction that we're moving as the value of the parameter is increasing. But here, it would be moving right to left, because this derivative of the x parametric equation would be negative, and t equals b would end up here. So as long as the x doesn't change direction, we can still talk about the area under the curve. Area. Area. All right, so now all we have to do is figure out how to set up the integral. Now the basis of the integral is to integrate the y from the left to right. Well, y is usually a function of x, but I wanted to write it as y instead of writing f of x because we're about to transform this into parametric equations. And the transformation is actually pretty simple. Keep in mind that in parametric equations, your y is some equation of the parameter, some function of the parameter, y of t. Whereas your x is also some other function of the parameter, we'll say x of t. To make the substitution, we just have to put in what we know. And what we need to know, we know what y equals, y is equal to that. So we would integrate the y parametric equation, but what would we replace dx with? Well, to find dx, let's take the derivative of this and write dx dt is equal to x prime of t. You know, the derivative of x with respect to t. If we solve that for dx, we would get dx equals x prime t times dt. So this would go in for the place of the dx. This dx would become all that. X prime t dt. And since we're integrating with respect to t, we need to integrate from the leftmost t value to the rightmost t value. The rightmost t value here is a, the leftmost t value is a, the rightmost t value is b. So it's almost like just a substitution. Replace y with what it equals, replace dx with what it equals. And in the case that the derivative of the x is negative, so that the curve is being traced out from right to left, it's almost exactly the same thing. We would still, I meant to write area equals in front of this. We would still replace the y with y of t, it's a parametric equation. We would still replace the dx with x prime t d of t, or dt, the derivative of the x parametric equation, but we're still integrating from left to right. And in terms of t values, the leftmost t value is b and the rightmost t value is a. So when it comes to setting up the integral for the area under a parametric curve, that's either always moving left or always moving right, but never changing directions horizontally. Just replace the y with what it equals and replace the dx with the derivative of the x function. Just really be careful that you set up the limits of integration correctly. If your x derivative is positive, it's from left to right, lowest t value to highest t value. But if your x derivative is negative, then it's from the highest t value to the lowest t value. Just remember, you always think about it moving from left to right. In the next example, we'll set up and evaluate some integrals to calculate the area under a curve. Gee, I wonder what curve we're going to use.